So, the Ampere's law in differential form, it is curl of B equal to mu naught J, and in integral form this is B dot dl is equal to mu naught times I enclosed. Now, this equation is perfect and is very useful in finding magnetic field due to some current distributions, but then evaluating this integral, this is valid in all cases of steady currents and all that, but then evaluation of this integral may not be simple, and for that certain kind of symmetry requirements are there, so that we can evaluate this, and if current distributions have those symmetries, then of course it gives us results very easily. The first thing we need is the direction of B. The direction of B should be known either by symmetry or using Biot-Savart law or in whatever way, then only you can really work it out. So, some examples and it will be clear. So, the first example is simple that we do in class 12, that you have a long wire carrying a current I, and you need the magnetic field because of this at a point P at some distance, let us say S. This is our z axis and S axis will be depending on P, drop a perpendicular from the field point P on the z axis, and that is S direction. This is S direction, this is S direction, and this distance is S. We had solved this problem completely, we know the result using Biot-Savart law. Now, we can, in this case we can apply this equation to get that final result. First we will have to know the direction of B, and for that the simplest is to use the Biot-Savart law. dB is equal to mu naught by 4 pi, and then I dl and cross r minus r prime divided by r minus r prime cube. We are only interested in knowing the direction, magnitude we will get from here. So, for direction, this is the vector which will give us direction. So, you take any element anywhere, any element, this is your dl vector because this is the direction of current. So, this is your dl vector, and this r minus r prime vector is here from this point A where you are taking the element, and then join this point P, and this is this r minus r prime vector. So, what we have to do? Take cross product. So, one vector is this way, another vector is this way, and then the cross product. So, you turn the first vector towards the second vector, and then you can see that we are, if you assume it will be screw, then we are going inside, and therefore, the direction of this cross product is perpendicular to the board and going inside. And remember, what direction is this? This is S cap direction, this is the direction of S, this is Z, and then it is S, phi and Z. So, going into the board is what? Is Z cross S, right? Z cross S, Z cross S, that will give you that direction, and that is phi cap. So, this will be in the phi cap direction. The magnetic field due to this element is in phi cap direction, and does not matter you take the element here or you take the element here or you take the element here, is the same story, is the same story. If you take it here, if you take your A here, this is the dl vector, this is dl vector, and this is the point, then this will be r minus r prime AP. AP this direction, and dl is in this direction. So, once again if you do the cross product of this dl vector and this r minus r prime, it is going into the board. So, the direction is phi cap direction. From any element the direction is going inside the board, and hence the net field is also inside the board. So, this is this much preparation was needed before coming to this. Now to get the magnitude of this B, here what we can do is we can draw a circle. You understand this circle is horizontal. So, half semicircle is here and the other half is behind the board. So, this is a circle of this kind, this is a circle of this kind, this is the circle, here is our board, and this is the wire, this is the current, long straight wire, and then this is the curve on which we will evaluate this Ampere's law. And if you are here, then this is S direction, this is phi direction. If you are here, then this is S direction, this is phi direction. If you are here, then this is S direction and this is phi direction. So, S and phi directions, they will keep changing as you go from here. On this we will evaluate B dot dl, and this circle is of that type, it's perpendicular to the z axis and it is circle. Now, since it is all at same distance, all these are radii of the circle. So, and you only have this current here, this is to be considered, no other current is around. Therefore, the magnitude of B here should be same as magnitude here or magnitude here or magnitude here or magnitude here or magnitude here, right. So, once again if you come to this, if this is the current and this is a long current, this is a long current, then what is the difference between this point and this point? Why should magnetic field be larger here and smaller here? They are all equidistant from this wire. So, the magnitude is same and the direction is phi cap. So, we can write this integration B dot dl as B vector is magnitude of B and phi cap. The direction of this is phi cap, unit vector phi cap, and the magnitude is B. So, this we can write this way, and dl vector also is in that same phi cap direction. If you are here, then it is going like this. If you are here, then it is going like this. If you are here, it is going like this. So, dl vector is also these are the dl vectors, these are the dl vectors. These are all in phi cap direction, they are all in phi cap direction. So, this dl vector also I can write as dl and phi cap. Then phi cap dot phi cap is 1, they are all unit vectors, and so it is B, magnitude of B and magnitude of dl. Now, magnitude of B is same everywhere on this circle, and therefore, I can take it out from the integration. It is constant, it does not change, the same B here, same B here, same B here, same B here. So, this you can write as B taken out and it is dl, and this is magnitude dl, remember magnitude dl, we have already taken the direction here. So, what you have to add here, dl, length dl, plus length dl, plus length dl, plus length dl, plus length dl. So, if you do it on this entire curve, it will be just B times the perimeter of the circle, 2 pi s. S is the radius, S is the radius of the circle, this point is at a distance s, and then with this same radius we have drawn this circle. So, this is how the left hand side is evaluated. Now, the steps are very important. From the vectors, we have gone to the magnitudes, and the magnitude is constant as you go along that curve, along that circle. Therefore, we could take it out. These things are important. Otherwise, if it is varying at different places, then this step will not do. So, this is our left hand side. What is right hand side? How much is the current crossing the area enclosed by the circle? And this is the positive side, this is the negative side. So, from negative side to positive side, how much current is crossing this area, since there is only one wire and that is crossing, and therefore, this is just I. So, the right hand side is mu naught times this current I, whatever current is here, and therefore, B is equal to mu naught I divided by 2 pi s. And since we know the direction phi cap, so B is mu naught I divided by 2 pi s phi cap. This result we had, this magnitude we have gotten from our Bhatt-Savart law. Okay. So, the integration has become very simple. The integration has become very simple. That time we had all that 3 by 2 and all powers and all that. Now, next example I can take is of the surface current. We talked about this. If we have in xy plane, large plane, infinite plane, and we have a current of this kind, and the current density is given by k. So, if you take a perpendicular line here of length dl, then the current crossing this line, that di, that is k times dl, that is how the k is defined. So, we had already solved this problem using Bhatt-Savart law, and now we will do it using this Ampere's law, and let us write the perspective of yz plane. So, y direction is this, z direction is this, and x direction is perpendicular like this. Okay. So, the entire surface on which the current is there is this is the surface, and this is xy plane, and in x direction we have current, right. So, that current we denote by these points, by these dots like this. So, this is a way to tell that the direction is perpendicular to the plane of the drawing. This is the plane of the drawing. So, the direction is perpendicular to this plane and it is coming out of this plane. So, that is the meaning of these dots. If it is going inside, if something which has direction going inside the plane of the drawing, we denote that by crosses. You put crosses here, and that tells that okay, the direction is going into the board, this is coming out of the board. So, that is the convention. Now, if I want to know the, let us say the magnetic field due to this whole thing here at some point, then and I want to use this Ampere's law, So, I have to evaluate this integration, and therefore, first I should know the direction, and for direction once again we will make use of Bhatt-Savart law, and let us say this is the foot of perpendicular, and from this point you go some distance this side and look at this current here. Then you go same distance on the other side, 1 2 3 4, 1 2 3 4, and then look at this current here. These two currents you look at it. Now, what is the magnetic field due to this current? It is not isolated wires. This entire, on this entire surface you have current. So, when I am writing this, I mean something like this, some small width here and some small width here. So, with this much of strip of current, what is the magnetic field here? So, this is the same situation as this long wire, and I am asking at some distance what is the magnetic field. So, here is a long wire, coming like this in x direction, small width, and then for that I am asking what is the direction of magnetic field here. So, we know from Biot-Savart's law, we have done just now, we have done that if this is the wire and here is the point, then you connect it this way, and then your right hand thumb rule, current, the thumb should be in the direction of current, it is coming out of the board, and then the fingers are curling this way, so it is perpendicular to this and fingers are curling this way. So, this will be dB because of this. And then similar exercise with this current. Here the current is like this, narrow strip, long current outside the board and inside the board also, infinite length, and because of this I need magnetic field here, the direction of magnetic field here. So, once again we will put thumb in the direction of current and the finger should go here and the fingers are curling this way, So, you join it this way and then drop a perpendicular, and these two which have equal magnitude, and then the resultant of these two will be in this direction, and this is the direction of B, it is in minus j cap direction. This was y axis, so this direction is j cap and this direction is minus j cap. Do a similar exercise for points below this, and there also you find that the direction of magnetic field will be now plus j cap, the direction of B dB will be like this. So, this is because of this one and this is because of this one, and this is the resultant for these two, but this entire current can be divided in such pairs, this pair, equidistant from this point. And so, because of the entire surface current also, the magnetic field here is in minus j cap direction, and similarly here combine everything and you get that the final magnetic field is in plus j cap directions. This much we should know before we can apply Ampere's law in integral form. Now come here, this is the equation, B dot dl is equal to mu naught times I enclosed. Okay, so once we have worked out the direction, I can remove all these things, make neat and clean space, and then I take a loop which is a line here, then a line here, then a line here and a line here, right. This is the loop and I put arrow here. From this side, looking from this side, this is the loop which is anti-clockwise. So, this area vector will be in this direction, this is the positive direction, and the space behind the blackboard will be the negative direction. So, we will work on this loop and here we will evaluate this B dot dl. So, start from here and look at this length. All these points are at the same height from this xy plane. So, whatever is the magnetic field here, same magnitude here, same magnitude here, same magnitude here. So, for this entire length, the direction of the magnetic field is constant, minus j cap, and the magnitude is also constant, say capital B. So, this whole integral, let me call it ABCD. So, on AB, if I do it on AB, first. So, from here to here B dot dl. Now, we have worked out that B is in this direction minus j cap and dl is also in the same direction. So, B dot dl is just in the magnitude of B and the magnitude of dl. So, this I can write as B dl, and B is same from here to here. So, it is B and then dl, and if you add dl, all these dl's, what you get is this length AB. So, it is that length AB, call it L. So, into L, that is our on AB. Then comes BC, on BC. So, on BC, B dot dl. Here B is in minus j cap direction, minus j cap direction. We do not know the magnitude yet, but it is all in minus j cap direction, right? And dl is here, this is dl, this is dl. So, B dot dl will be 0. So, here this B dot dl will be 0. Then comes CD, then comes a CD, on CD. So, if I look at this CD, then we have dl is now, see, this is the arrow. So, this is the arrow and this is the arrow. So, dl is going this way dl is going, and below this xy plane the magnetic field is also in plus j cap direction, dl is also in plus j cap direction. So, the same rule for CD, integration of B dot dl is equal to B dl is equal to B into L, and then on dA this integration is 0, B dot dl is 0, not circle, this on dA. So, on dA, these are dl's, this is dl, this is dl, this is dl, this is dl, and here the magnetic field is in this direction and here it is in this direction. Okay. So, on this it is 0. Now, you add all four AB, BC, CD, DA, and that will be integration B dot dl on this entire loop, and that is BL plus 0, and that is 2 times B into L. So, that is our left hand side. What is right hand side? Right hand side is mu naught times I enclosed. So, what is that I enclosed? Here is the loop, and remember the current is coming this way from behind the board, it is coming this way, and all these dots show that the current is coming out of the board. Now, all this current which is coming out, this much current is crossing this area enclosed by the loop. Okay, this much current is crossing from the negative side to the positive side, and it goes through this area. This is not going through the area, this is not going through the area. So, it is this current. And how much is this current? If the current is going in this direction, surface current, then the surface current density we define, perpendicular to that you take a line, and K times dl will be the current. So, here this length is L, from here to here the length is L, and this length is perpendicular to the current direction. It is this length in y direction, current is coming this way. So, this current will be, which is crossing this area, will be just K times and then L, K times L, and these two are equal, these two are equal. So, what you get? You get 2BL is equal to mu naught K times L, L cancels out, B is mu naught K by 2, and B vector is equal to mu naught K by 2 minus j cap minus j cap for points above the plane, that xy plane, and this is mu naught k by 2 j cap for points below the xy plane. Okay, so that is how we can get this magnetic field due to current, surface current in xy plane. One more example I will talk, and that is a solenoid, long solenoid. So, long solenoid. So, what is that? You have a coil essentially of some small width, small radius, and then large number of turns, very long, and then the current is going like this, is going like this, and we assume in this, for this derivation we will assume that it goes up to infinity, and from each turn you have a current. So, that same current is going this way. So, that is called a solenoid or a coil, long coil. Okay, so, like this, from each turn you have this current. Now, we want magnetic field due to this current at points outside, inside, and so on. So, first thing is to describe this current. Current is I, but then how many turns per unit length are there, that is important. If you have a solenoid like this, then the situation is different. If you have solenoid like this, then the situation is different. Same current, it may be same current. All right. So, number of turns per unit length is an important parameter, and that is, let us say, small n. Let small n is number of turns per unit length. Which length? Along the axis of the solenoid. We are talking of this length. If this length is, say, delta L, and then the number of turns here to here is delta n, 1 turn, 2 turns, 3 turns, 4 turns, 5 turns. So, number of turns in this delta L length is delta n, that small n is delta n over delta L. So, that is our small n, number of turns per unit length, and unit length means not along, not this length, not the length of the turns, not the length of the wire, it is the length along the axis. So, that is n. Now, if it is a long solenoid, then you take it that outside the magnetic field is 0. Not very simple to prove, and therefore, I am avoiding the proof. You take it granted that if it is a very, very long solenoid, then the magnetic field outside here, here, here will be 0, and it is the inside for which we have to work. You already know the result. You already know the result. You know that for a long solenoid, the magnetic field is along the axis, and the value is mu naught n I, and that is in the direction of this solenoid axis. But how do I derive that? So, that is very important, and that will give good practice of using this Ampere's law. So, outside we will take it to be 0, and inside the first task is to find the direction of the magnetic field, because if we want to use this B dot dl equal to mu naught times I enclosed to evaluate this integration, to evaluate this integration I need the direction. So, B can be written as, suppose I have a point here and I need magnetic field here. So, B can be written as Bs S cap plus B phi phi cap plus Bz z cap. So, first we have to look at these components and see what can be the direction. So, we will work out from the symmetry and the result will be that this component has to be 0 and this component has to be 0 and it is only in the z direction. But beforehand we cannot say that, we have to justify that. So, next class we will do that, we will see that from the symmetry how can we tell what is the direction of this B, and once we know the direction of B here, then we will work out using Ampere's law how much should be the magnetic field, and you know the answer, finally it will come out to be this. Next lecture.